Okay, so it's great pleasure to have Babak from Tsinghua Yau Center. He's going to tell us about the elliptic quantum curves of class SK, please.
Yeah. Okay, yeah. Thanks a lot, Satoshi, for inviting me to give this talk. And yeah, this is a talk on elliptic quantum curves of class SK based on a paper with the same name, which appeared a couple of months ago in August, together with yeah, my postdocs. Hello, do you hear me still?
Yes, I can.
Your screen went dark, or not
dark.
dark,
But yes. I just switch off the camera.
I see. Okay. So this is based on work with Jin Chen and Marcos Sperling, who are here at Tsinghua, and also Hee-Chul Kim. And yeah, so let me then begin. So the main subject of this talk are, as the title suggests, quantum curves. So in order to describe these, I would first have to start with normal algebraic curves. They are given, of course, by such an equation. So we have an equation in C star times C star of, and this is a polynomial, this h in the variables x and y, equal to 0. And you can think of these variables x and y as exponentiated variables, so that they take values on the annulus or on the equivalently, topologically equivalent on the cylinder. But the exponential is valued in C itself. So there are different ways to think about this. But if we use these exponentiated variables, the curve is a hypersurface in C star times C star. Okay, and what kind of curves are we interested in practice? So historically, these kinds of curves, which were later quantized, arise in different contexts. Let's say maybe the most well-known one is in the context of knot theory and the A polynomial. And basically there it describes to you the moduli space of SL2C flat connections on knot complements. And you can think of these X and Ys as holonomies. So if you have a knot complement, then the boundary of this knot complement is topologically a torus. And you can think of the connection, and then you can take a basically a loop operator eigenvalue, a loop expectation value of that connection around these generating cycles of the torus. And then they have to basically satisfy certain conditions at the boundary of this three manifold. And so the moduli space is then given by this kind of algebraic curve. And so this is one thing. Of course, more generally, we have also situations of in geometric quantization where you have moduli spaces of certain solitons, which are Riemann surfaces. And then this equation for you describes then the classical moduli space of the object, which we then want to quantize in the next step. So yeah, and this quantization is done, as I said before, these x and y variables are exponentiated variables. And the quantization is done by taking the logarithm of these and promoting the logarithm to operators such that they satisfy this type of Heisenberg algebra here. And the exponentiated variables can be then thought of as satisfying this commutation relation, where Q is the exponential of this H bar here. And in this context, the X here, the X operator, just tells you, that the log X is just the position, and this Y here will be the exponential of the momentum. And as we know, the exponential of the momentum is then nothing else than a shift operator. It's a translation operator, and it translates the wave function or whatever it acts on by H bar. And in this sense, then you basically have to, in a very controlled way, take this polynomial here, which describes this algebraic curve, and quantize it by promoting these variables to these operators satisfying these relations. But then you have to be careful about normal ordering and issues like that. So this whole polynomial will become Q-dependent. And there are prescriptions of how to do this. And in fact, in our case, we will naturally kind of derive this expression, and we will, we don't have to start, I mean, from such an expression, we will immediately derive this expression, but then we can compare to the classical expression. And the constraint here becomes then a quantum operator relation, such that this h bar acting on some wave function is 0. So you can think of this as an Hamiltonian acting on some wave function with eigenvalue 0. And as I said before, in this SLNC Chern-Simons theory, this psi is then a partition function of this not complement. And we will be more interested in the context of mirror symmetry, where psi is the open topological string partition function of a certain Calabi-Yau geometry or mirror Calabi-Yau geometry. So let's see how this arises. So in our case, we will be interested in non-compact elliptic Calabi-Yau manifolds M of the following type. So here, as you can see, these are by now maybe famous because they classify 60 SCFTs, these Calabi-Yau manifolds. And each of these lines here represents, in this case, a -2 curve, and such that the discriminant locus of this elliptic Calabi-Yau is this chain of -2 curves, which you can see here. So by -2, I mean a curve with self-intersection -2. And the elliptic fiber degenerates over this discriminant loci as an IK Kodaira singularity. And this is a non-compact curve on the left, and this is a non-compact curve on the right. And this Calabi-Yau manifolds are important, as I said before, for 60 SCFTs, namely, you take F theory on this manifold, and this will give rise to a 61,0 SCFT of type SK. So in this particular case, where we have n-1 of such -2 curves, we get n M5 branes extended along T2 times R4, and they are probing a ZK singularity. So the type of the singularity in this geometric realization, the type, I mean, it's a C2 mod ZK singularity, which these M5 branes are probing in the perpendicular space. And this type here in the F theory dual picture is given by the degeneration of the elliptic fiber. So this is, this is also called an A-type conformal meta theory. And now we are not so much interested in this manifold itself, but for our context, the mirror Calabi-Yau W, basically this W is my notation for mirror of M, is basically flipped. And it's a cone over a Riemann surface. And this was derived in a previous paper. And for this particular Calabi-Yau manifolds, the mirror geometry is a cone over such a Riemann surface, where we have a polynomial in this t variable, which is again taking an exponentiated variable. So it is taking values on the annulus. And the coefficients here are important because now this type of Riemann surface, these coefficients are not ordinary polynomials in Z, but they are Jacobi forms. So one of these variables, we have two variables again, W and Z. So T is the exponential of W, and Z is the other variable. This now lives on the torus. So this is the crucial kind of new ingredient here, that we have the ZW coordinates living on T2 times C now. And then this equation is, of course, a hypersurface in this space. Okay, so this is roughly how we can think about these equations. And these Jacobi forms, they are products in our particular case, which is given by this geometry. One finds that they are products of theta functions. of Riemann theta functions over the torus. And this can be all explicitly worked out, as we will also see in the following. So now we have derived this kind of classical geometry. And now I want to quantize this. But before talking about that, we maybe have to say, what do we mean when we quantize this? Or what object are we in fact quantizing from the string theory or gauge theory point of view? Namely, so quantization itself is, of course, done in this way. We will promote these operators to variables, satisfying, again, this relation. And then this y becomes a shift operator, as before. And then we have this kind of equation. But what does it correspond to? What is the interpretation of this? Well, I mean, the way we approach this and the way you can think about this is in the sense of defect partition functions. So in the 60 SCFT, there will be eventually a codimension 2 defect partition function, which we call psi. But in order to see why it will satisfy such an equation, let's employ mirror symmetry. If you use mirror symmetry, you will see that the mirror Calabi-Yau is this Riemann surface or cone over this Riemann surface, and the defect will be mapped to a brane wrapping a special Lagrangian manifold, which is intersecting this Riemann surface at a point. So it is transverse to it and along these conical directions, and it intersects it at a particular point. And so the moduli space, the classical moduli space of this brane will be this Riemann surface. And if we want to go over to quantization and to then the partition function of the brane, of course, will be a state and a Hilbert space, which arises from quantizing this moduli space or phase space. So in this sense, the Riemann surface is the phase space of this Lagrangian brane, and we are going to quantize it in order to describe the partition function in terms of this wave function. Okay, and so this partition function, I mean, here I call it z, but basically I label it now with this psi variable, and in 60, in the original maybe interpretation, as I said, this will then correspond to a defect operator extended along T2 times R2 and localized at a fixed point because we have the geometry is T2 times R4. So this will be a defect localized on T2 times R2 and point like on the other R2. And then the claim is that, in fact, we're going to obtain this particular, let's say, if we now specify that the case of 2M5 branes probing a zk singularity, then the claim is that we obtain this kind of quantum curve. Okay, so again, you can think of this as in the previous setup. This rises from the quantization of the previous polynomial. There is this constant piece here, which plays an important role. And as we will see in our formulas, we can derive that this is an expectation value of a codimension 4 defect operator. So here, this kind of equation will ties up together several pieces, namely it ties up codimension 2 defect operators realized in terms of branes and codimension 4 defect operators. Namely, this guy is the codimension 2 defect partition function, and this guy is the expectation value of the codimension 4 operator, and they all will be basically satisfying this type of equation, which again can be very nicely interpreted in this mirror Calabi-Yau geometry.
I have one question.
Any questions? Yeah.
Yes.
Yeah.
When you say codimension 4 defect operators, it's wrap on T2?
Yes. Sorry. Yeah, that's good. It is wrapping only the T2 and not the R2 or anything, and it's point-like on the R4.
Point-like R4. Okay.
So usually the way it works, we will put this geometry on the omega background, and then you have this epsilon1 and epsilon2 corresponding to two R2 planes and the R4, and then one of these, the codimension 2 defect, will be specified by one of these epsilon planes, and the codimension 4 operator is at the origin of R4.
Okay. So this psi only includes codimension 2 defect operator, but not the codimension 4.
Yes.
Or does it?
No, but as I will argue later, this product which you can see here, W times psi, this is a this can be actually thought of as a codimension 2 for
I see. Like a couple
operator,
system.
joint operator.
Couple system. Somehow. So when you add
the crucial point is that this equation arises in the NS limit, in the Nekrasov-Shatarashvili limit of omega background, as I will argue later, and only there it will factorize. Otherwise, it does not factorize.
Okay. So it's more like elliptic version of QQ character.
Yes.
Okay.
Exactly. That's another name for it. Yeah. Yeah. Any other questions? Okay, then let me continue. So how do we describe these defects and how do we compute these partition functions? Well, now we had these two frameworks. We have thought of the system of the 60 theory as a 2M5 range probing a ZK singularity. We have thought about it as an F theory compactification on an elliptic Calabi-Yau. But we can also think about this as in terms of a brane setup, where we have these 2M5 branes become two NS5 branes, and the ZK singularity becomes these 6 branes stretched between them. And this is then the brane setup giving rise to the same theory. And in this setup, we can easily characterize the defect and also compute it. Namely, the way it arises, these are Higgsing defects. So you can think of a theory which has, so the ZK singularity will give rise to a UK or SUK gauge group in the bulk. And you can think of these defects we are interested in arising from Higgsing. So you start with an SUK plus 1 theory, and then you Higgs it to an SUK theory by giving that to such an operator. And this is pictorially shown here. You take you start with K plus 1 D6 branes, but then you move away one of these D6 branes, and you insert this D4 tilde between the NS5 and this D6. And then this is then the defect, the codimension 2 defect, if you specify the dimensions as it should wrap correctly. And this is then, they call this Higgsing defect. And because of this nice brane realization, we can then, actually compute the partition function of this defect. And the way it works is that from the previous formalism developed for 60 theories, we know that if the 60 theory is wrapped on a torus, then the Nekrasov partition function of the system can be computed in terms of summing over contributions of strings wrapping the torus. So in the brane system, the strings can be thought of as D2 branes stretched between the NS5 branes, and counting the contributions of all these strings gives you the full 60 partition function. And in this case, of course, we will still want to compute the full 60 partition function, but now in the presence of this defect. So now if we want to compute these string contributions, there will be contributions which come from on the world volume theory of these D2 branes. There will be some strings connecting this D2 and D4 tildes. So the 2D quiver of these D2 branes will change. So if you for a moment think of this piece here, this diagonal piece here removed, then the quiver shown here is the so-called M strings or orbifolds of M strings quiver, which allows you to compute the world volume theory of 60 strings on the tensor branch. And this is the effective description of that world volume. So the UL here is the number of strings or the number of D2 branes, and these are chiral multiplets, these are Fermi multiplets, and these here again the dashed lines are Fermi multiplets, and the solid lines are chiral multiplets. And you see that indeed you have this kind of quiver, and this can be all deduced, and this has been done in the past. and then you compute the elliptic genus of this kind of 2D theory, and you get the contribution of that string, of L strings, let's say. And then you increase L and then sum over all these to obtain the full 6D partition function. So this is the known picture. And now we have to modify it slightly because of the presence of this defect, right? And the way it works is that we basically will include, I mean, there will be a gain from, as I said, from the fields connecting the D2 brane and the D4. There will be then chiral and Fermi multiplets corresponding to this U1X flavor symmetry. The flavor symmetry is the symmetry of this defect here. And this is basically then how we have to modify our defect partition function. So I will say in a minute how these guys look like, but basically the 6D partition function in the presence of the defect will have a perturbative piece. And then as said before, this is completely analogous to the previous story, a piece coming from the strings, which is the sum here. So these L is the string number. So these strings are kind of instanton contributions. And the ZLs here are these elliptic genera of this 2D quiver. Okay. So in the following, we need to compute these elliptic genera, sum them over, and then obtain the defect partition function. And if you do this, then you notice that, in fact, since the quiver almost looks the same, the defect one loop contribution, so for computing the elliptic genus, you always compute the one loop contribution, and then you have to integrate it over the Wilson lines of the 2D gauge theory. And so these are the cartons of the 2D gauge group. If you want, you have to integrate over those, this one loop contribution. And now this one loop contribution, this is the original one, which we had for the imp strings. But now we get this piece, which comes from the defect. So this is exactly the piece which comes from these, this extra chiral and Fermi multiplets connecting to this D4 tilde. Right.
I have one
and
question.
so yeah.
Can you go back to previous slides?
Mm-hmm. Yeah.
So which direction is T2 direction?
Which direction is what?
T2. You consider 60.
And the torus.
Huh?
This is in the world volume of these NS5 branes. It's not depicted here.
Okay.
But it is basically in this world volume theory of these NS5 branes.
Mm-hmm.
And you can think of coordinates x0 and x1. And these are then toric. So basically, in this picture, you will have to this direction is circular. So this is circular, this direction, the x1. But there is another circular direction which is not depicted here.
Oh, I see. So you just consider T2 as the intersection between D2 and the NS5?
Absolutely, yeah, and
okay.
D6, yeah, yeah.
And you compute the elliptic genus on this T2, right?
Absolutely.
Okay.
Yeah.
And so in the next slide, you write the B contribution comes from this U1X.
This is exactly, this V comes from this U1X. Exactly. Okay. This is the defect.
Okay, thank you very much.
Yeah. And this one is the original one. So this one is the contribution of the vector, chiral, and Fermi of the original 2D quiver theory, which was a 0,4 supersymmetric theory. And now we have this defect contribution, which is a ratio of these theta functions. And the theta functions come, the numerator comes from the Fermi multiplet, the denominator from the chiral multiplet. And you see they carry charges under these U1s, which are denoted by epsilon1 and epsilon2, because there are these rotations, U1 rotations, which rotate each of these planes in the R4. And now the defect will be then labeled by R and S, as you can see. So this comes from the fact whether what kind of which space this kind of D4 branes are supposed to fill out. So usually we will just take one of them to be 0 and the other one to be 1. So that means that this defect is wrapping the epsilon2 plane, if you want, and is not extended along the other one. But you can have more complicated defects. So the general defect is of an RS type, and then it will, these Fermi multiplets will carry these types of charges under this epsilon1 and epsilon2. And this U is again, as I said, the carton of the worldsheet of the string, of the gauge theory and the worldsheet of the string. And yeah, so this is then what we have. And
sorry.
yeah, questions?
Is this type of defect related to the type in AGT corresponding to the degenerate insertion on the Riemann surface?
Which type?
Those corresponding to degenerate vertex operator on the Riemann surface.
Oh, that's I think those are different types of defect, because in this case the defect is wrapping the whole torus and the Riemann surface or the Gayotto curve would be corresponding to that kind of torus. So it is an operator which is wrapping that. It's not point-like there. I mean, of course, in the mirror description, as I said, this defect becomes a Lagrangian brane, which is point-like on that. So yeah, in that sense, yeah, you're right. I mean, in the mirror geometry, if you think about it from the point of view of the mirror geometry, this is exactly such an operator. Yeah.
Okay, thanks.
It's point-like on this Riemann surface. Yeah. And okay, so good. Any other question to these codimension 2 defects? So if not, then I will proceed, because as I said before, we also need codimension 4 defects. So here we have again our system, these D4 tilde branes, where these codimension 2 defects, as you can see, they will wrap the torus direction 0 and 1. They are extended along this 4, 5 directions and point like here. And they also one leg at this direction here, which is perpendicular to the whole thing. Now we're going to insert another brane, namely D4 prime, and this is just point-like on R4 and fully extended along these perpendicular directions, which were not depicted in the picture, and this wrap this T2. So it is, from the 60 point of view, it is a Wilson surface because it's wrapping this T2, but it's point-like, so it's codimension 4. It's point-like on R4. And the quiver is very similar to the codimension 2 one. So this, I'm always showing here the quivers of only the codimension 2 defect in the previous case, and in this case, only the codimension 4 defect. And it's very similar. So you have again the fugacity attached to this defect, and you have now again these chiral and Fermi multiplets. But these kinds of defects, they preserve 0,4 supersymmetry. So you have a whole hypermultiplets here from the supersymmetry consideration. So you have 2 chiral and 2 Fermi multiplets. That's the main difference. And you have also this kind of extra piece, which is not gauge, or which is not charged under these gauge symmetries, which is basically coming from Fermi multiplets between these two. And therefore, we get the original one loop contribution, plus these extra pieces, namely the 2 chiral and the 2 Fermi fields, which are here denoted by these products of theta functions. So this plus minus notation means that this is actually, the numerator is a product of 2 theta functions. The denominator is again a product of 2 theta functions. And there is some perturbative contribution here, which comes from this, this Fermi multiplet, which is now, since these guys are charged under the bulk gauge group, we have k theta functions because the bulk gauge group was SUK, and the AJs here are the fugacities of that gauge symmetry, which is a flavor symmetry from the 2D point of view. So this is the full extra contribution which you have, and you have to multiply it with this U1 loop, and then again compute the integrals, right? So that is how we compute this codimension 4 defect. Okay.
So here,
questions here.
So here you ignore U1x.
Yeah, I don't put U1x here. I have just a. So if you want, this is a coupled codimension. This is a coupled 2D60 system.
Okay. Okay.
We'll describe.
Okay. Thanks.
No, the 4D part is not included. Okay.
Can I have a question here?
Yeah.
So So I guess that this type 2A is from this is obtained from this A type of the conformal matter layer. Yeah, I mean, essentially in M theory, that's the transverse geometry is like a C2 mod out ZK, right?
Exactly, yeah.
And then you reduce on one cycle on this, I think it's on this transverse geometry. I'm just saying that this the S1 that you take should be here. Should the radius of this S1 should go to an infinity line.
Oh, you mean the S1 in the transverse direction, you mean?
Yes.
Yeah. That's true, absolutely right. Yeah.
And that is a strong coupling of this type 2, and how could you justify this? I mean, this partition function you calculate.
Sure. I mean, if these fibranes are on top of each other, this will be a strong coupling if you want. So of course, then we have no gauge theory. I mean, we have no effective description of these fibranes. But what I'm doing here is we are going to the tensor branch. Okay. If you go to the tensor branch, you go again away from the interacting fixed point of the 6D theory, and you have basically moved on to the tensor branch, and there things have a string theory description. So we can use string theory to then describe everything on this tensor branch. At this SCFT fixed point, yeah, you're right. We don't know anything there.
Okay, and another question is that somehow you mentioned this is this 2D equivalence M string.
Yes.
And so let's list n equals 2. Yeah. So my question is that, I mean, it seems to me that it can be generalized to some general type of n, like a mod out ZK.
Yeah, sure. I mean, these kind of things have been done in the past, and there are all kinds of quivers describing all kinds of 6D theories. And but it's not always clear what the brane realization is. So so that's why in this case, this is the simplest case one starts with, where everything is, the brane realization is clear. We can describe the defect and this brane picture and so on and so forth.
Okay, thanks.
Okay, so then let me proceed. So again, we compute the elliptic genus by taking this particular product here. So this everything is now included in this Z Wilson 1 loop. Then I have to integrate over these U variables, and then the full 60 partition function in the presence of this Wilson operator, Wilson surface operator, is the perturbative piece of 60, the perturbative piece of this defect, plus this sum over these instantons. And this is then computed in this way by computing these elliptic genera. And then we can define the defect expectation value. And the expectation value is basically taking this whole thing here and dividing it by the pure 60 partition function without the presence of any defect. So then you will see that this piece will cancel, this piece will remain, and then there will be in the denominator the contribution of the strings in the pure 60 setup. And I can expand this in Q phi, and you will see that, let's say, to order Q phi, you will have this contribution to this operator, which is namely the elliptic genus in the presence of this Wilson subtracted by the usual elliptic genus of one string. So this is becomes important because these things then will have finite values in the Nekrasov-Shatashvili limit. Otherwise, it would be not finite, and we would have infinities. So this is a kind of correct normalization. And this is the correct operator which we need to consider. And so now we have introduced all kinds of defects and pure partition functions and so on. So let me summarize this and also highlight the role of this quantum curve there in this picture. So we can start with this 6D theory. This K here is just a label that is this the fibranes probing ZK singularity. And if we add this codimension to defect, we have a coupled 60-40 system. The 40 part is the defect wrapping the T2 times R2, and the 60 is just our 60 theory. And we showed how to compute this partition function. We also saw how to add a codimension 4 defect only. Now, not a codimension 2, just a codimension 4 defect. This is a coupled 60 2D system. The 2D stands for the Wilson surface, and they both depend on the fugacities of these defects, let's say. Moreover, this is what we have not considered so far. We can add codimension 2 plus 4 defects. So we have a coupled 6D, 4D, and 2D system. And this is actually what turns out to be crucial, but we don't need to compute this, in fact, because this thing will simplify. And the claim is now, and this is what I will be showing, that there will be a difference operator. We will derive a difference operator such that if it acts on the 60-40, namely the codimension 2 partition function, it will generate the 60-40 2D partition function, this coupled thing. But since we have never talked before of how to compute this guy, it's a bit hard to test this. But the crucial point here is that we are going to take the NS limit. So if you take the NS limit, you expect this kind of factorization. So what you will get is that your Wilson surface expectation, this 60, the coupled partition, 60, 40, 2D, will be just a product of this Wilson surface times the coupled 60, 40. And the reason for that is that basically you see the way it works is that if you have these codimension 2 defect, you have on R4, you have these two R2 planes, and this defect is wrapping one of these R2 planes, it's point-like on the other, and the codimension 4 defect is point-like on both. And as long as you turn on both epsilon 1 and epsilon 2, you cannot move these away. You can not touch this system, otherwise you would break the symmetry, because this symmetry, this configuration perfectly respects these two U1 symmetries, because you can rotate here, nothing changes. You can rotate here because they are at the origin, nothing will change. But as soon as you send the epsilon parameter corresponding to this plane to 0, you can move one of these branes, one of these defects away from the other. And since once you do this, this is corresponding to the NS limit, you can move the codimension 2 defect, let's say, away from the other one. And then this kind of thing will factorize. This is basically the consequence of this factorization. I mean, the reason for this factorization. And then once we rewrite this equation in this way, you can see that, of course, the codimension 2 partition function will then be annihilated by this combined operator, which is the difference operator subtracted by this Wilson surface expectation value. And as we will see later, this is just a quantized Seiberg-Witten curve, because yeah, I mean, this is actually equal to the Seiberg-Witten curve if you think of it as an algebraic curve, let's say. And so this is the picture which I'm going to now explain how to arrive at. So yeah, any questions hereby? Okay, so then let me proceed. So the way we compute this is, again, the defect part here has the main piece of the defect part is the string piece. So we have to sum over all these string contributions. And this kind of sum, and there is, of course, each of these contains an integral here of these u parameters. This combined sum and integral can be actually written in terms of a path integral. So this is the result, what one gets. So the crucial piece here is this Rho function. This is the eigenvalue density. So this is a sum over delta functions. And yeah, so you basically have this will be only non-zero if u is equal to this u piece. And you basically have you have to integrate over all these kinds of guys here, and you have to also integrate them over u. And if you if you take this d here to be this particular ratio of theta functions, and this q, this one, so this, you can think of this d arising from the gauge multiplus of the 2D theory, and this is the matter fields of the 2D theory, of the 2D quiver. And if you plug this in and use these definitions, you will see that you will get the original expression for the elliptic genus. It's just rewritten and now expressed as a path integral over these densities here. So if you, I mean, you see that you have this is some convolution between these two densities, but effectively, if you plug everything in, you will just obtain the usual elliptic genus expression. And this lambda prime is a Lagrange multiplier, which is a remnant of the fact that we want to enforce at the path integral. In the path integral, we will have contributions of this form. And this factor here is just an abbreviation for this ratio of theta functions, which only depend on epsilon 1 and epsilon 2. So this is the picture you get. So you see, you get a kind of matrix model, because this can be thought of a quadratic matrix model if you want. This rho these are these eigenvalues, or the eigenvalue density is quadratic, and there's also this linear piece coupled to this potential here. And these kinds of problems, it is then known how to solve. And in the following, we're going to evaluate this particular path integral. Okay, so yeah, I mean that's the main crucial idea here, to rewrite everything in this way. But if you want to evaluate a path integral, usually you need to start with some saddle point. So you usually in gauge theory, you have some weak coupling, and you can then do Feynman expansions and so on. And the way it works here is very similar. What we're going to do is we're going to send this epsilon 2 to 0, and then this particular piece will be expanded in this way. And we have these are abbreviations for these ratios here. And this whole quadratic piece here will become, yeah, it can be rewritten in this way, where this sum, I mean, this is just rewritten in this way because this whole thing should be symmetric under exchange of u and u prime. So you have to rewrite it in this way. And then this can be expanded in epsilon 2, and later on we will send epsilon 2 to 0. We're going to use all these expressions. These all arise from an epsilon 2 expansion of the original kernels here. And so this log of d can be written in terms of this g1, and then this g1 and g2 are arising from this epsilon 2 expansion here. And then what you can do is you can see that the whole, well, what you see first of all is that the whole partition function, since because of this piece is 1 over epsilon 2, there will be a 1 over epsilon 2 square in front. So since epsilon 2 is going to 0, we can argue that we can do a saddle point approximation. So this is a kind of, if you want, the weak coupling limit. And so since this is then, so then all these other terms you can neglect. I mean, of course, we're going to collect so many epsilon 2 contributions such that overall we have 1 over epsilon 2 in front. And what you get is then this kind of a picture. So you have the full defect partition function in terms of the path integral. And we want to compute the saddle point. So we do variation with respect to these eigenvalue densities. Then we have the same thing times 1 over epsilon 2 times this piece. This comes from the exponential. This comes down from the exponential. And we have a 1 over epsilon 2 because, yeah, that's how the saddle point arises. And this guy here is this matter part evaluated at epsilon 2 is equal to 0. And if you then want to compute the saddle point, you have to equate this to 0. If you equate this to 0, you will get this as saddle point equation. So the dominant contribution to these eigenvalue densities has to satisfy this equation, this integral equation here. And now we can a bit massage this equation and make it bring it to a nicer form. So what we're going to do is we're going to introduce these y variables here. These are convolutions of this density with a kernel given by these theta. This is the derivative of the log of this theta function here. And the reason is that because as seen before, these guys all contain theta functions. So all these, the previous elliptic genus is always the product of theta functions. So it will always boil down to these kinds of building blocks, because this is the eventually this is the main building block, this y function. And to rewrite the saddle point equation, we're going to also use this omega function, which is this particular ratio of these y functions and this piece here, which is only dependent on the 60 gauge fugacities. And then you can see that the saddle point equation, plugging in the expressions for G1 here, This is just this L. L was theta prime over theta, right? And you see that the derivative of the logarithm of theta is theta prime over theta. So this is how we cover the previous terms. Then you can see that this saddle point equation will be just this particular equation. So now we have rewritten it in terms of an equation containing these omegas, and this will have only solutions. So we have to then solve these equations for these parameters u star. So we have to basically compute the corresponding omega and the corresponding u stars, where this will be 0. This will not be everywhere 0. This will be 0 for certain parameters, for certain choices here denoted by u star.
Sorry, does this equation relate to some kind of beta ansatz equation?
Yes. I mean, this is all related to some integrable system, but I'm not going to go into that direction, but mainly focus on this gauge theory or 6D theory interpretation. But of course, yeah, there is another orthogonal viewpoint where one can consider connecting to these integrable systems and beta ansatz equation. But this is exactly of that type, and this can be solved exactly as those equations are solved. Yes.
Where does this complicated trick comes from? I saw some similar trick done by Negros-Shatashevili, maybe.
Well, yeah, it is done maybe by Negros. I mean, this kind of path integral picture. Rewrite everything with this eigenvalue density. This trick is due to Nekrasov and Okunkov.
Oh, okay. I see. So it's kind of some technique from matrix model or something. Where does the idea? So idea come from matrix model or something?
Yes, because that's of course Okunkov has won the Fields Medal on this stuff. So he basically combined methods in statistical mechanics with algebraic geometry, and that's basically what is happening here.
Okay, impressive. So wow, impressive.
Yeah. So you can basically that is the story here, and then you obtain the
sorry.
Yeah.
So, could you tell me what the integrable system is? The corresponding.
It is the Schneider elliptic integrable system, but I don't know the details. I'm no expert there, but yeah, that is some integrable system of that style.
Okay, thank you.
Elliptic integral systems of Boysen, Schneider. Yeah. So yeah, you can rewrite it in this way, and this M function is a contribution of these matter fugacities or flavor fugacities of the 6D theory only. And as I said, the gauge fugacities are in this P0, which is contained in this omega. Now we have to solve this equation, but before we do that, let's remark that, as said before, I mean, there is only this only vanishes at these certain points u star, not everywhere. But you can now form for any other point, you can form this particular ratio. You divide this piece by omega. And if you go through all the steps in the derivation, you will realize that this u star is not only a 0 of this, but it will be also a 0 of the denominator. I mean, actually, the thing is that this is a bit shifted. So the 0, I mean, this is not exactly the previous piece, but if you can see, we have shifted everything by minus epsilon 1. And so this guarantees that the zeros of this piece here, which will be occurring as here, will cancel against the zeros of this guy, which will occur for u star plus epsilon 1. And so therefore, this piece is totally holomorphic and has no poles. And so the poles all will cancel. And just looking at the properties, because everything was formulated in terms of theta functions, and you can show that this guy is a certain degree section over the torus, because u is a parameter, is an elliptic parameter on the torus, and this is a degree k section on the torus. So from a very general point of view, it can be always written as a product of k theta functions. where these roots here, ELs, they can be very complicated. They depend on all kinds of fugacity parameters, of course, but generically it can be always written in this way. And if we do this, so since we know that this ratio will then take this form, and we define this to be this function p, we can then rewrite this as p, multiply everything by omega, and rewrite then this equation here in this way. And this is then our crucial equation, because now in the following we will show that this is actually a difference equation. And so to see that this is a difference equation, we have to promote the exponential defect fugacities to non-commutative parameters. This is the old story here, which we basically had seen before, but now h bar is, the role of h bar is played by this remaining parameter epsilon1. Epsilon2, as said before, is sent to 0. It's gone, but epsilon1 will play the role of h bar in this quantum curve. And y is then, as said before, a shift operator in this way. And now observe the following crucial fact, namely, if you apply this y operator on the 60-40 system, namely the codimension 2 defect partition function, you can show very easily, just by using this path integral representation at the saddle point, you can show that this operator acting on this just generates for you this omega, which we defined previously, times this defect partition function. So this omega suddenly pops up here, or said differently, let's fix the defect to be of type 0,1, so S is just 1. Then you see that the ratio of this y applied on this guy divided by this is just omega. So omega is the ratio of y applied at the defect partition function divided by the original defect partition function. So now you can take the saddle point equation and multiply it, and multiplied by the original defect partition function to get rid of the denominators, because omega is always a ratio, you want to get rid of the denominators. Then you can easily convince yourself that the saddle point equation is just this difference equation. So this is what you ultimately will arrive at. And this p here, now if you go back to the original claim which I made at the beginning, we want to reinterpret this p as the expectation value of the Wilson surface, or codimension 4 operator. And as we will see, this is indeed true. So yeah, the way this is again working is that we're gonna do it in a Q-phi expansion and then check these claims order by order. So we can now take this defect partition function, write it of course in this way, but the p can be also written in this way, because as said before, we could write it as a product of these theta functions, but these ELs, they can be very complicated. They will depend on Q-phi and so on. So you can always expand this function in this way. Now we plug in these expansions into the original difference equation. It will take this form. And then we have, of course, our original claim with the p replaced by the Wilson surface. And the Wilson surface has also this kind of string expansion, right? We saw how to compute it in terms of these elliptic genera. And then the claim is that actually these PLs here are equal to these Wilson surface contributions for L strings. While I said before, we had these two variables, z and x. X was the fugacity of the codimension 2 defect. Z was the fugacity of the codimension 4 defect. But they are going to be identified now in this way. If you identify them in this way, then indeed we observe this equality. And this is something which can be, first let's rewrite then our original equation in this way. So we identify this p with the Wilson expectation value, Wilson surface expectation value, by identifying z with x in this way. And that's then our difference equation. And then we evaluate it order by order to check it. So you can, of course, expand to order 0 in Q-phi. Then you obtain this equation. So you see that then this way you can fix P0. So P0 is computed from the perturbative piece of the defect contribution then, just by applying this y operator to it. And at one string level, we will obtain this particular equation. And if you combine this equation with this one, so you see already that this piece will vanish, and you are left with this one. And if you then plug in again the result for P0, you can solve for P1. And for P1, you will get this result. So P1 is then generated by applying these Y operators to the one string contribution of the defect. So the codimension 4 defect is generated this way recursively from the codimension 2 defect by applying these Y operators on it. This is the crucial observation. And if you solve it in this way, this P, you see that this matches with the computation of the Wilson surface defect at one string from the elliptic genus. So all these things can be shown to be exactly equal, and you can continue it to higher order and it will work. One last thing I want to say is that, of course, this particular thing which we have derived is we can test it in different ways. Namely, let's apply it to the simplest possible theory, namely the 62,0 A1 theory of 2M5 branes without any perpendicular singularity. That one is actually dual upon circle compactification to 5D SU2 maximal super-Young Mills. So you can now start from that theory, from maximal super-Young Mills, and then do the defect of that theory, and it should also match. So this is a dual viewpoint, and this is just how we parameterize these parameters here. But the crucial point is that now I want to start with this. This is the maximal super-Young Mills of the SU2 gauge group. In order to take a defect here, you can start with this theory and then Higgs it, defect Higgs it, and to obtain this. And one can then go through analogous computations, and that was done before for this theory. And so first of all, let me say that these two theories are just identical. I mean, one can observe it at the level of partition functions, that the 6D and the 5D theories are just equal if one identifies the fugacities in this particular way. These are 5D fugacities here. This A capital A are SU21, SU2 gauge fugacities of these two SU2 gauge nodes. These are the fugacities of bifundamental flavors. These are the instanton fugacities Y and Q over Y of this affine quiver theory. And if you identify the 5D and 6D parameters in this way, you can show that the 6D and 5D partition functions are equal. So if you Higgs both theories to obtain the defect partition functions in both cases, they should satisfy the same equation. And this is something, the Higgsing of this circular quiver was done previously by Bullimore, Kim, and Koroteyev. And they had computed this Z1,1, which they call the monodromy defect. And this is basically the Higgsing procedure to go from this quiver to this quiver plus defect. And so they computed this, and they showed that this guy satisfies this type of difference equation. But now, if we use these identifications here, we can see that in fact this is exactly the difference operator which we obtain in our formulas. Where now in our case it generalizes to all the 61,0 theories, but as for the 2,0 theories, it is identical to their operator. If we do these identifications, if the 2,0 Wilson surface is identified with their SU2 Wilson surface, and we also identify the the defect fugacity with Y was the instanton fugacity of the circular quiver, and this shift operator, our 6D shift operator, is identified with this eta parameter times basically the shift of their shift operator, which is the shift in the instanton fugacity. And because the way it works is that our defect fugacity is embedded into our flavor symmetries, and the flavor symmetries are identified with the 5D instanton fugacity in this dual picture. So that's why this map comes about. And then one can check that indeed these two difference operators are equal, which is a neat check of our results. But in the way we set it up, we can of course do now all the 1,0 theories also as well, which were not done before. So of class SK. Okay, so let me summarize. We started by introducing the concept or notion of elliptic quantum curves which are quantum curves arising from a quantization of these algebraic equations into this operator equation, where one of the parameters here, z, is elliptic. Then we showed that, that in the case of 60 SCFTs compactified on a torus, codimension 2 defect operators lead to such elliptic quantum curves. For the case of amphibranes probing ZK singularities, we had a brane construction at our disposal which we could use in terms of a path integral to effectively compute the difference equation in the NS limit. And we also found that the eigenvalues of our quantum curve difference equation correspond to codimension 4 surface operators. And we checked this against a dual description of the 62,0 theory of 2M fibranes. Namely, that can be rewritten in terms of 5D maximal super Young mills. So we have this defect in a torus-compactified 60 theory, but we can also take the circle-compactified 5D super Young mills with SU2 gauge group plus defect, and the two results matched. And what needs to be done in the future is, this is work in progress, to generalize these difference operators and quantum curves to the case of the E string, and also to other minimal 60 SCFTs. So yeah, with this, I would like to then end. Yeah, thank you very much.
Thank you very much. Questions?
Hi, Babak.
Hi, Shin.
Hi. Great. So maybe let's talk first. So I have a question for you, because you said there are general RS type defect, but in your computation you actually said maybe like R equal to 0. I'm wondering whether if you turn on R, which is now 0, is there a similar difference equation for that defect partition function?
We didn't look into that, but it is expected, yeah, that there are similar different equations for that as well.
But I look at the perturbative contribution of that type. Yeah. I know that there is a constraint for the defect partition function, which means if you expand it in terms of Ogilvy-Vafa invariance, in the refined case, there are only epsilon 1 pole or epsilon 2 poles.
Yeah. Only
one type, but I look at the formula. I mean, perturbative contribution, it contains 2 type. I mean, what I mean is that if you turn on both R and S,
one would expect, you say, for this kind of Ogilvy-Vafa invariance.
Right. So I'm wondering, you said there should be another difference equation for general
the main point is that if you have R, S, it's not easy to take the NS limit. You will probably have to take a combination of epsilon 1 and epsilon 2 or something. I don't know. I mean, I haven't thought about this here, because the defect, 0,1 defect, is just wrapping one of the R2 planes. You can see that it's point-like on the other, so you can switch off one of these epsilon parameters. So it is very, very natural which epsilon parameter to turn off. But if you have this combined defect, then I think the story becomes more complicated.
Oh, I see. Okay, thank you.
Any other questions?
So the K appear in this quantum curve in the product of set function. That's the only place that appears.
Let me go back to the form of this operator. It is basically this one. For 2 and 5 branes, you have this, and the K appears in this product.
K appear in the product. Oh, I see. When you take K equal to 1, you get the 2,0? That's what you mean? How do you get 2,0 in your case?
K equal to 1, you would get 2,0. Yes.
Okay, that's the limit you take, and to compare 5D theory by using duality. I see.
Right.
I see. I see. Yeah, this really look like QQ character of kind of pure YAMLs. If you go to 5D, is it true? No, not pure YAML.
Yeah, this is this equation.
Okay,
This one.
I see. I see. I see. So,
And here the elliptic parameter is y, because there is no elliptic. Only elliptic, basically circular direction is the quiver itself, right? Because the quiver is now affine.
Yep.
The quiver is not affine, right? But
Yeah.
torus. But here the quiver is itself is affine.
Yeah.
So if you shift the instant on fugacities, you will come back, kind of, you know.
I see.
So that's why this data function, the argument is y, which is the instant on fugacity.
I see.
This becomes elliptic.
I see. It's more like okay. The maximally super means 5D. You have
Yes,
again,
yes,
right?
this is that thing.
Okay.
Yeah.
Okay. 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 Thank you very much. Any other question from audience?
Yeah, I have some maybe a naive question. So do I mean I know that of course you calculate this one. It shows that this is it is like this one. But I wonder that is there some intuitive things that make you start this program to say that the quantum curve is tied with these codimension 2 defects?
Well, the quantum curve should be from the mirror symmetry expectation value. From the symmetry expectation, you expect that, because as I said, if you have to take the Calabi-Yau point of view, go to the mirror geometry, then the Seiberg-Witten curve appears in the mirror, and then the defect also becomes a Lagrangian intersecting this mirror curve at a point. So,
so you mean
quantize this, if you want to.
So you mean
that is the intuition behind it.
Okay, so it's like this, exactly like maybe you know this exponential network that this mirror curve is the modular space of these codimension 2 defects.
Exactly.
Okay.
Exactly. It's a modular.
Yes.
And then whenever you quantize this, you describe the partition function as a state in the Hilbert space, and that's why the partition function becomes the state.
Right. Yes.
Hi. May I ask you a question?
Yes. Hi.
So in your slides, there are some index I and X stand for, I think, for the defect operator. Could this I and S be negative integer?
Oh, actually, we took them to be natural numbers, so I don't think so. But yeah.
I see. Thank you.
We basically only looked at natural numbers, and then we only specified to the 0,1 case.
I see. So another question is that is there some symmetries in the partition function? For example, it changes epsilon1 to negative minus epsilon 2 and epsilon 2 to minus epsilon 1, just like the exchange symmetries in Kuhn-Wolfer formula.
Yeah. Sure. Whatever. I mean, you should have all the symmetries, but note that the defect, the way we insert the defect will break this kind of symmetries, because the defect will then be wrapping only one of these epsilon planes, right? And not the other.
Yeah.
So in a sense, the defect will break the symmetry. So some the symmetries will be reduced.
But this is I remember that in Haghighat paper for the refined Tsinghua theory, they said that the partition function for the Q brane is equal to the partition function of anti-T brane. So the symmetry, exchange symmetry between T and
in that sense, there is symmetry, of course, but that means that if you do this exchange, you go from one partition function to another.
Yeah.
Partition function, I mean, in this sense, I mean, yeah. If this is equal to that, if you do the symmetry, you might go from 1 up to the anti. Yeah, maybe to go from the 0,1 to the minus 1,0 defect or something like that, right?
Yeah. I see that. Thanks.
Okay. There are many questions, so let's thank the Babak again. Thank you very much. Stop recording.